Hi, all you crazy kids out there. Hope you're continuing to do well. Today we are going to continue our study of exponential functions. Yesterday we went over some basics of exponential functions, what they are, domain, range, crazy things like that. Today we are going to look at how they are used in the real world. So let's say, for example, you have a large city whose population was about 4.6 million people in the year 2010, and it's growing at a rate of 1.3% over the next 4 years. What exponential function models the population of the city over that 4-year period? Well, let's take a look. So what we're going to do is we're going to start with our old friend y equals. And then we're going to start with 4.6 because remember we talked about yesterday the first number in the exponential function, the a value, is the y-intercept. And so that's the starting value of the function. So in this case, if we're starting with 4.6 million people, then our function is going to start with the number 4.6. All right, here's the fun part. Then we're going to go times 1 plus and then what I'm going to do is I'm going to take the 1.3% and change it into a decimal by moving the decimal 2 places to the left. So that would be 0.013, and then I'm going to raise that all to the x power, because remember that in an exponential function, what makes it unique is that the exponent is a variable. So all of the things in this function are pretty easy to understand. The 4.6 comes from the starting population. The 0.013 is 1.3% as a decimal, and the x is the exponent. The only question that I get from students a lot is why is there a 1 there? The 1 is there because that represents the initial population. So if I were to distribute this 4.6, for example, the first thing I would do would be to multiply it by 1. That would give me the 4.6 million people that I'm starting with, and then I would add on to that 4.6 times 0.013. That would give me the additional 1.3% population growth, and so if I combine those, that gives me the starting population plus the population growth. Right? Okay, so now that we have a function, we can use that to answer the question, if the population continues to grow at the same rate, what will the population be in 2040? Well, I'm glad you asked. So let's go y equals, and then we were starting with 4.6 million people. So y equals 4.6 times 1, again that's because that's the original amount of people, plus 0.013, that's 1.3% as a decimal, and then now we are raising that to the 30th power because this was our starting population in 2010, and 2040 is 30 years later. So then if I jump over to my other computer that does have internet access and type that into Desmos, then that gives me an answer of about 6.77 million people. Okay? So that's what that looks like. So actually exponential functions are super easy to use. You just need to know the starting value. You're always going to have a 1 here, and then this is the percent that the thing is growing. So if you want to pause the video and try this on your own at home, you can. Give you a second to do that, and then I'll go over the answer with you. Alright, so the way this looks is they have given us a function this time. Now you'll notice this time the thing that we're multiplying by is less than 1. That's because we're talking about the value of an object, and the value of this object, a printer, is decreasing, and so we're multiplying by a number less than 1 so that it's going down. So this right here, this 0.93, what that tells me is that the object is worth 93% of what it was worth the year before. And another way to think about that is to understand that that means the value of the object is going down by 7% per year. So what is the value of the printer after 10 years? Again, I'm going to go 30 times 0.93, this time to the 10th power. And then again, I will pop over here to Desmos, and sadly, for your computer, in 10 years, your 3D printer is only worth $14.52. But I'm thinking when I look at this again that, I mean, the starting value here is 30. So I know you can't get a 3D printer for only $30. So maybe this is like $30,000, but that seems like a pretty fancy printer. So who knows? All right, next question says, does the printer lose more of its value in the first 10 years or in the second 10 years after it was purchased? Well, in the first 10 years, we just figured out that it went from an initial value of $30, I guess, to a new value of $14.52. So that means it has lost, over the course of the first 10 years, it has lost $15.48 in value. Let's see what happens to the value of the computer over the course of the next 10 years. So now I'm going to see how much it's going to be worth 20 years from its original purchase date. And to do that, I'm going to go 0.93 to the 20th power. And I'm going to have to cheat. And so that turns out to be $7.03 would be how much it would be worth in 20 years. So if after 10 years it was worth $14.52, and 10 years after that it was worth $7.03, that means over the next 10 years it only lost $7.49 worth of value. So you can see that over the course of the first 10 years it went down from $30 to $14.52. That's a loss in value of $15.48. Over the course of the next 10 years, it went down from $14.52 to $7.03. That's only a loss of $7.49, so it lost more value in the first 10 years. And when we were looking at the graphs yesterday, if you think about this graph, you might be able to see that exponential functions go down a lot, and then they start to level off. And so from year 0 to 10, it's typically going to lose more value than from year 10 to 20. Okay, so this is a summary of what we just were talking about. We can have two different kinds of exponential functions. One is called exponential growth. That is when the value of the object, or the size of the object or whatever, is increasing. So that's when we're multiplying by a number larger than 1. Or we can have exponential decay, which is when things are decreasing. In that case, we would take the percent and change it to a decimal like we did before, and then go 1 minus that. So then this would give us a number less than 1, and then that would be decreasing or decay. And then a fancy vocab word is the growth or decay factor, is this number here that you're multiplying by each time. All right, let's play again. So a car was purchased for $24,000. The function y equals 24 times 0.8x can be used to model the value of the car in thousands of dollars x years after it was purchased. Does the function represent exponential growth or exponential decay? Well, in this case, since we are multiplying by 0.8 each time, which is a number that's less than 1, this would be an example of exponential decay. For part B, what is the rate of decay for this function? The decay rate is equal to b, which in this case is 0.8. That's what we're multiplying by each time. What that means is the car is worth 80% of what it was last year. And again, another way to think about that is that its value is decreasing by 20% each year. So it's losing 20% of its value, which means to figure out what it's worth, we have to multiply by 0.8. Okay, good stuff. All right, graph the function on a reasonable domain. I'll give you a reasonable domain. So here's our, white is a good color. Here is our axes. And we're starting at 24 and we're going down by 0.8 each time. So let's just randomly call this 24, and then we're going down by 0.8, or no, I'm sorry, we're going down by 0.2, we're saving 0.8, so that makes me feel like it's not going to go down like uber cray-cray or anything. So there's a graph. What does the Y-intercept represent? The Y-intercept is the initial value of the car. When will the value of the car be about 5,000? Okay, so to do that, I would need to have my graphing calculator so I could see where the graphs cross. So if I do that on Desmos here off to the side, sorry, this is super awkward, and make a graph of the original function, and then I want to know when the value of the car would be around $5,000. That would be what we would want to figure out when that whole thing is equal to 5, because remember the values are in thousands of dollars. On my little calculator over here off to the side, when I graphed the two things, so I have the graph of this function, and then I have a graph of perfectly drawn horizontal line at y equals 5, then that tells me I can click on the intersection point on Desmosis and see that that'll happen after about 7.03 years. And one of the things that we're going to do later in this chapter is we're going to learn how to do the math so that we do not have to use a graph to figure out that answer. But that is something for another day. Okay, so once again, there's one for you to try on your own. If you are so inclined, go ahead and pause the video, work through this problem, and then I will answer the question with you. All right, so this one says 220 hawks were released into a region on January 2nd, 2016. That's a lot of hawks, if you ask me. We have a function there that models the hawk population, so you can see because we're multiplying by 1.05, the population is going up by about 5% each year. So when it says, is the population increasing or decreasing, we can say that it is increasing by 5% each year, and the place that we got that from is the 1.05. So the 1 again is the original number of hawks, and then the 0.05 is the 5% that are being added each time. Okay, so in what year will the hawks reach 280? So again, this is a little awkward for me to do because you guys can't see the graph, but if I type this onto my calculadora, and I get the original graph, and then I want to see where does that cross with 280. In this case, the graph is going up. Oh, if only you could see the graph. It's just beautiful. Just kidding. 4.943 years. And again, that's just putting the graph on Desmos, graphing the line y equals 280, clicking on the point of intersection. Ooh, this looks exciting. All right, this one says a museum purchased a painting and a sculpture in the same year. Their changing values are modeled as shown. So for some reason, in this case right here, we have a function. So this one was purchased for $50,000, and it's going up in value by about 7.5% each year. Then for this one, we only have a graph. I hope this isn't the painting that they purchased, because if they paid $40,000 for this painting, they really got ripped off. Anyway, then 5 years later, this is worth $64,400. So let's find the average rate of change of the value of each artwork over the 5-year period. So I'm going to do this one first because it's a little bit easier. So in this case, the value of the painting went up. 5 years later, it was worth $64.4 $1,000. It started at $40,000, so that means its value went up by $24,400 over the course of 5 years. So if I go $24,400 divided by 5, I'm feeling like that's going to give me, I had it. If I divided by 10, that'd be 2.4, so divided by 5 is going to be twice that, or 4.88. There we go. So it's going to go up by, it went up by on average $1,000 per year. Okay? All right, for this other guy over here, we need a little bit more information. We know that its starting value is $50,000, but then I need to figure out what the value of that is going to be 5 years from now, so I can compare that with the other one. So on my calculadora, I'm going to type in 50 times 1.075 to the 5th power. And so that means 5 years later, this weird sculpture is worth $71,780. So if I subtract off of that the $50,000 that it was worth to start with, then that means that it has gone up by 21.78. And then if I divide that by 5, that shows me that the sculpture has not gone up by quite as much. 21.78 divided by 5. A little bit too much for my big brain today. It's 4.356 thousands of dollars per year. Man. So this one was valued less in the beginning, and 5 years later it's still valued less. This one was worth $50,000 to start with, and 5 years later it was worth over $71,000, but it's going up by less each year. So eventually that one's going to be worth more than the sculpture. So there we go. That's the answer to this little try-it question. Will the value of the painting ever surpass the value of the sculpture? Yes. The value of the painting is going up by more per year than the sculpture. So eventually it will be worth más. And again, we'll learn some math later to figure out how to do that. All right, so that's all we got. That's this whole section. We talked about exponential growth functions. That's what this graph of exponential growth looks like. That's when the b value is greater than 1. Exponential decay, graph's going down. That's when the thing we're multiplying by is less than 1. Here is our general equation for an exponential function. Domain we talked about yesterday, and behavior we talked about yesterday, and some ways to make the different functions. Alright, so here are a handful of problems for you to try as enrichment if you are so inclined. I'm going to go ahead and stop this video, upload it to YouTube, and then make another exciting video of myself going through these problems with you. Alright, see you later.